So Rutherford did what we call the gold foil experiment, right? At this point, our model of the atom is J.J. Thomson's, where he has a big fluffy atom where you've got a positive sea of pudding with all these negative electrons. He had the mass kind of all spread out in the atom. They called it the plum pudding model. Rutherford kind of said they're like big squishy atoms, right? Because we know the mass and we know the volume. And so if we assume it's all spread out, it makes for a fairly more like doughy kind of thing, right? So what Rutherford did in the gold foil experiment is he put a sample of cesium in a chamber that was radioactive. So it was releasing alpha particles. And alpha particles are big, positively charged radiation. They release helium nuclei. So two protons and two protons and two neutrons get released and they fire out this way. They're really big and they don't do damage to people, right? Because just a few layers of skin can stop them, right? But he fired it at a very thin sheet of gold foil. So this gold foil, right? It's made out of gold and it's about 100 atoms thick. It's only 100 atoms thick. And what he was expecting to have happen was they all went through and then they fanned out a little bit, kind of like shooting water at a screen, right? Where it might fan out a little bit, but it all kind of stays right here because they're kind of marshmallowy atoms. So you should just be able to push right through them. And most of the time, that's exactly what happened. Most of the time, in fact, 7,999 times out of 8,000, nothing happened at all, right? They just go straight through and hit on a phosphor screen right here without even the deflection that he was expecting. They just went straight through like that. 7,999 times out of 8,000, they just go straight through. But one time out of 8,000, they deflect wildly, like clear over to here, or clear back to here, or clear back like this, and they hit a screen that's over there. And he said, well, that's only 1 in 8,000 times. That's like firing an 18-pound cannonball at a piece of tissue paper and having it bounce back and hit you. So even though it happened very seldomly, he's like, that's weird. That doesn't match with the plum pudding model of the atom, right? The fact that 1 in 8,000 times it happened tells us that whatever you're doing here, it's very uncommon. So if you're hitting something, whatever you're hitting is tiny, tiny, tiny. Imagine if half the time it was doing that. Well, that would mean it was taking up about half the space, right? Well, 1 in 8,000 times it's happening. And by the way, we're passing 100 atoms to try and get that to happen. So it's kind of effectively like having not 1 in 8,000, but 1 in 800,000 times it's bouncing off, right? If it was one atom thick, right? Like 1 in 800,000 times. So he said, well, that means that this plum pudding model of the atom is wrong. Again, he fired alpha particles at gold foil. Most of them passed straight through. A very small number were deflected wildly. So he said, well, since alpha particles are positive, this beam of stuff is positively charged, and some fancy calculus that we don't have to get into based on how they deflected here. He said, whatever we're hitting is positively charged. And that's where all the mass is, because most of the stuff is going straight through. So he took this model of the atom and he said, well, let's change that model of the atom a little bit. Let's shrink all the positive, right? Remember, this was all doughy positive. Let's shrink all that positive right into the nucleus. And then we'll leave the electrons out here, and we're going to put all the mass in the nucleus, right? So the key idea is that he has a nucleus now. It's positive, and all the mass is in that nucleus. So then you've got these electrons out here outside of the nucleus. And that was where he had trouble, is he said, well, I know the mass and the positive charges in the nucleus, but we know these electrons are still negative and removable. But what are the electrons doing? Because if they're just sitting there, well, they'd be drawn to the nucleus, and then they'd be stuck in there. And if they were orbiting like a planet, classical physics says when you spin a charged particle, it releases energy. Well, these things aren't naturally just releasing energy all the time. So he released his model saying there's something wrong with my model. It doesn't quite work. It almost works. It's better, but it's still not quite right. And if we get something that's better, even if it's not quite right, it's still pretty good, right? So the important things you would definitely want to include would be stuff about the gold foil experiment, which you can certainly read more about than what I just said, and Rutherford's model of the atom. Be careful when you look at Rutherford's model of the atom. Alpha particles will often be shown flying through these. Those aren't part of his model. They're how we learned about his model. So don't include arrows going through here and bouncing off of stuff. All right, hopefully that helps.